Exploring the Solar System Part 4, Exoplanets. What used to be called exosolar planets or extrasolar planets. Planets around other stars, not planets around our star. So, why bother in the first place? Why look for exoplanets? How do you go about finding them? Finding planets around our sun is relatively easy. You look up in the night sky and there are bright dots up there. But how do you find planets around other stars? And is it possible to tell whether any of those planets out there have life? And again, I ask the question, where do we go from here? What's next? So why look for exoplanets in the first place? Well, one of the reasons is we're asking the question, is our solar system typical? We know that we've got a solar system with Mercury, Venus, our planet Earth, Mars, Jupiter, Saturn, Uranus, Neptune. But is that typical? Can we expect a similar mix of planets if we look at what's going on around other stars? Are there other Earth-like planets out there? Are there other planets that look like Earth? If there are solar systems out there, would we expect them to have an Earth-like planet, or is that a rarity? And if there are Earth-like planets, or even if there aren't, are there any signs of life out there in the galaxy? Hopefully, studying other solar systems will help us understand our own. So how do we go about finding exoplanets? Well, there are a number of different techniques, and I don't really have time to go through all of them in detail. So I'm going to say a little bit about 3 discovery methods. One is radial velocity. In other words, if a planet is going around a star, it makes the star wobble, and we may not be able to see the planet, but we might be able to detect the wobble of the star. If the star comes towards us or away from us, it'll change the spectrum. In other words, we take the colour of that star, we break the light down into all of its colours, and we can see signs of the star coming towards us or moving away from us. It's called the Doppler effect. So it's called the radial velocity, but it's basically looking for the wobble of the star. The other possibility that, depending on how the solar system is oriented, it might be a planet moves in front of the star, and hence the light of the star is temporarily blocked or at least diminished. So a transit of a planet in front of a star, in other words, a shadow moving in front of the star, we might not be able to see the shadow, but we might be able to detect a drop in the light level. And finally, one possibility is direct imaging. Generally speaking, stars are much too bright to see any planets that happen to be close to them. But if we can block the light from the star, then maybe we can see tiny dots where the planets are close to the star. 2 other methods called microlensing, which bends light from distant objects, and astrometry, which means looking at the positions of stars and seeing if they're changing their positions. That's 2 other methods which haven't found that many planets, but I'll mention them in the handout, but I'm not going to mention them in the presentation itself. So let's have a look at those first 3 and see how they work. The first one is looking for wobbles, and this has been used for finding thousands of planets. If we imagine a planet going around a star, they both move around their common centre of gravity. So depending on the mass of the planet, the star will wobble a bit, and sometimes it'll move towards us and sometimes it'll move away from us. The little schematic at the bottom implies that maybe the light becomes a little redder or the light becomes a little bluer. It's not quite like that, but if I change to a slightly different graphic, if we imagine the sun is wobbling towards us or away from us as the planet is going around the sun, or the star I should say, then because the star is spending some of its time moving towards us or some of its time moving away from us, a so-called Doppler shift will change the spectrum, much like if you listen to a particular note like an ambulance, as it comes towards you and as it goes away from you, you hear a different pitch. It's the same idea. When we look at the spectrum, when we take the light from the star and break it into a spectrum, as the star comes towards us or away from us, we see features in the spectrum that get shifted towards the red end of the spectrum or towards the blue end of the spectrum, a so-called red shift or blue shift, And if the star is wobbling, we see this characteristic backwards and forwards motion of the features that we see in the spectrum of the star. So this has the advantage that we don't need to see the planet, we only need to pick up the light from the star, and spectroscopy can be enormously powerful and see tiny changes in the motion of a star, and hence pick up even relatively small planets, not necessarily huge planets like, for instance, a Jupiter-sized planet. The second method is the transit method, and again this has been used to find thousands of different exoplanets. What happens if a planet happens to move in front of the star? The light from the star, shown by the little cartoon on the left hand side there, the light from the star can drop. As long as we measure the output of the star, the light from the star, accurately enough, we can see even a small drop. Generally speaking, the planet is not going to be so huge that we see a 10% drop in the light level. It might be that we only see 0.5% or 1% drop in the light level from the star when a planet moves in front of the star. But as long as we measure the intensity of the starlight accurately enough, we can see tiny changes. And if the planet is rather large, as in the left-hand side, compared to rather small, as in the right-hand side, a big planet will simply block more light, and so we'll see a bigger dip. How long that dip takes depends on how fast the planet is moving around the star. But the depth of the dip, is it 1%, is it 2%, is it 0.5%, that gives us an idea of how big the planet is. So the first method, the idea of wobble, depends on how massive the planet is. But this method depends on physically how large the planet is in terms of how much starlight it blocks. If we see what we actually measure, that's what we would like to see, a change in starlight. What we actually measure is a whole load of data points of the starlight with a little bit of noise in there as well, and then we try and fit it to the best curve we can to tell us what the characteristics of that particular planet are. And the James Webb Space Telescope is particularly good at doing this because it has a very large mirror. It can collect a lot of light, and being in space, it's not affected by the Earth's atmosphere. And so we can get very accurate data from the star intensity, the intensity of starlight, the brightness of the star, if you like, and then we can see very clearly that it's dropped, even though it's dropped by a very tiny amount. That's 100% of the starlight, and mid-transit it's dropped to, what is it for this particular planet, 98.5%. So it's only dropped by 1.5%, but if we measure it very accurately, we can get a lot of very useful data out of a curve like this from the Hubble Space Telescope, and indeed from other Earth-based telescopes as well. The final method is block the light from the star. The star is really bright and it's very difficult to see any planet that happens to be right next door to the planet, right next door to the star. So what happens is inside the telescope there's a small so-called occulting disk, a small black circle blocks the light from the star as indicated here. We can imagine this is a really bright star and maybe there's some planets around it, but if we can somehow block the light from that star by blocking it out physically, then the fainter planets will hopefully show themselves. The star is going to be so bright there's bound to be some scattered light, which is represented by this rather fuzzy edge to the star. But if we see how it works in practice, here's a time lapse where the star in the middle has been blocked out by an occulting disk, and we're left with 4 small points of light. And if I run that particular animation again, you can see the one closest to the star is moving fastest and the ones furthest out are moving slowest, just like we see in our solar system. So this is actually taken over 12 years. So this was imaged time and time and time again, possibly on a weekly basis or a monthly basis over a period of years, and hence we can deduce the existence of a solar system here with at least 4 planets that are visible. How bright they are, well, that will depend on how reflective they are and how far they are from their host star. This is actually a relatively large solar system compared to ours. It even works if we're seeing the solar system edge on. Here, a large occulting disk in the middle is blocking the star, and you can see the planet shows itself when it appears on one side or when it appears on the other. Let's run that animation again. We can't see it when it's behind the disk, but if it's far enough from the star, we see it on one side, and as it's going round the star, we can see it when it pops up on the other side. Again, this is a time lapse taken over many, many months, a total of, what was it, 17 years for this particular time lapse. So these are planets quite a long way from their star, and they take quite a long time to go round their sun. It's a much more difficult problem to see planets which are close to their host star, because it's then difficult to block out the light from the star but still leave the planet, and they'll be going round a lot faster. Direct imaging works quite well for some systems. Here's a direct image from the James Webb Space Telescope. Again, right in the middle, a little black disk has blocked out the very bright star, and it's allowed the James Webb to image what's going on around that star. In this particular case, it appears not to be a solar system of individual planets. It appears to be a very dusty environment with a lot of rings. Perhaps this is a little bit like the asteroid belt around our solar system, and the Kuiper belt, which is a belt of icy objects beyond the orbit of Neptune. It's difficult to be sure, but we think this is possibly a solar system in the very early stages of formation, and the dusty environment here hasn't yet coalesced into individual planets, which it may do in due course. Not on the timescale that we can watch it, but perhaps over thousands or hundreds of thousands of years, this system will develop into an identifiable solar system. So what do we learn from the various planets that we can, in principle, study? It's fantastic if we can study a system using multiple techniques. Because remember, radial velocity, which is the wobble of a star, depends on how massive the planet is. Whereas if we're looking for shadows, transits of a disk in front of the star, how much the light dips will depend on the size. And also, if we look at the colour, if we split the light from the star into its colours, we can get information about the atmosphere of the planet. If we can do all of these, then we can get the mass and the size. That, of course, gives us an estimate of the density, because the mass in a given size effectively is a measure of the density. We would expect rocky planets to have quite a high density. We would expect a planet which is essentially water to have a lower density. And if it's a gas planet, well, maybe it might have a density less than water, like Saturn does, for instance. So the density gives us a way of telling what type of planet we have. And if we know how far it is from the planet to the host star, and we can effectively measure the temperature of the star by looking at its spectrum, if we know how far the planet is from the star, we can get an idea of how hot it is. And hence we can tell whether or not the planet is likely to be an ice planet, or a water planet, or a lava planet, depending on exactly what its surface temperature turns out to be. So all of these bits of information, when collected together, can give us a pretty good idea of what's going on a given planet. And we end up building a zoo of thousands upon thousands of planets. Don't take the pictures too literally. The sizes are approximately to scale with what we believe these exoplanet sizes are. The colours are a little bit of artistic license, and again the banding, we can't see the clouds on these planets, but these are artists' impression of what we think is the most likely appearance of these planets. So they are to scale in size, and they are positioned in this particular graphic on a scale with cold planets on the left, let's say minus 200 Celsius or so, and relatively hot planets on the right, the surface temperatures of various planets. One thing to bear in mind is this is not all of them. This is only a selection of 1,000 or so exoplanets. So far, something like somewhere between 5,000 and 6,000 planets have been found. We think there are far more out there, but we've only been looking at a certain number of stars to find these planets. In this particular graphic, in the bottom left-hand corner, let's blow it up to make it easier to see, there are a few interlopers because we've got here some planets from our own solar system. So we've got Jupiter, we've got Saturn, we've got Uranus, and we've got Neptune. They're there simply to sort of give you a little bit of an indication of scale, and perhaps to remind us that Jupiter is actually quite a big planet. There are some planets bigger than Jupiter, but not that many. Earth, Mars and Venus are also in this graphic, and I'll show you where they are in just a second. Because it's cold on the right and hot on the left, if we're interested in any planets which are in the Goldilocks zone, the range in which we think liquid water might exist, well, too far to the left, water is going to be frozen. Too far to the right, water is going to evaporate. So we would only expect to find liquid water in a relatively narrow temperature range. And if we compare with our own solar system, we find that Mars is too cold, Venus is too warm, but not surprisingly, Earth is in just the right place in the Goldilocks zone to have liquid water present. Now, maybe liquid water isn't required for life, but it is a very good start. So that's why a lot of people are concentrating their effort on looking at exoplanets that happen to be in that relatively narrow temperature range. Let's have a brief look at some of these other exoplanets. Which ones are worth noting? Well, I thought it was quite interesting to note that our nearest neighbour in the Alpha Centauri system, only 4 light years from Earth, even that has planets. If planets were rare, you wouldn't expect to have the coincidence that our immediate neighbour happens to have a planetary system. And the more we look, the more we come to the conclusion that planetary systems are indeed everywhere. They seem to be at least as common as 50-50. For any given star, there's a pretty good chance it has a planetary system. They are not rare structures. It's not like only 1 in a million stars actually has a solar system like ours. Solar systems exist almost everywhere. What other interesting objects have we got there? Well, there's one planet that's been found that appears to be very old. This planet exists around a very old star, and we assume that the planets were made at the same time as the star. It's very difficult to see how a star could be made, and then a long time later, along comes a planet. We believe the planets were always made at the same time as the star. So if the star is 12.7 billion years old, then the planet is as well. And this is going back a long way into the history of the universe. The universe is 13.8 billion years old. So this planet existed very early on in the early universe. So it looks like planets are not a recent invention, if you like. They're not a recent thing. Planets have been around almost as long as the universe has existed. In the top right, there's a planet with a very high surface temperature. It's way over on the right-hand side of this diagram here. And it has a temperature way above the few hundred Kelvin of the Earth's temperature. This is a few thousand Kelvin. And the one in the bottom right that looks a bit egg-shaped, that's not a very bad artist's drawing. That planet is egg-shaped because it's relatively close to its host star, only 4 million kilometers. Remember, the Earth is about 150 million kilometers from the Sun, so this is very close to the star it's orbiting, and because of that, it's actually being stretched out into an egg shape. What other planets have we got in here? One of the largest is this one. Goes by the wonderful name of HATP67b. They've got to find better names for these things, surely. This planet has something like 10 times the volume of Jupiter, but it appears to be less massive than Jupiter. So that means it must be a very low density object. It's been estimated from its size and from its mass that it must have the density of marshmallow or something like that. Many, many times less than the density of rock and many times less than the density of water. On the subject of names, yes, they're struggling to find the names of these planets, but they have at least come up with 1 or 2 interesting names. I think the prize for the best name has to be Coconuts 2b. What a great name. Cool companions on ultra-wide orbits is the sort of acronym that's coconuts. What they mean by ultra-wide orbits is planets at a huge distance from their host star. 7,500 astronomical units. 1 AU, 1 astronomical unit, is the distance from the Earth to the Sun. So this planet is further from its star by a factor of 7,500 times compared to the distance from us to the Sun. As a consequence, it takes a long time to orbit its host star. We take 1 year to go round the Sun. It takes about 1,000,000 years to go round its star. Amazing. I think the prize for the weirdest planet has to be this one, LHS 1140b. So small you can't see it there, so let's blow it up. It's an eyeball. Well, it looks a little bit like an eyeball. This artist's impression shows you what we think this one looks like. It appears to be cold enough for the surface to be basically ice. And yet it's relatively close to its star. That's not a contradiction because the star isn't very bright. It's not producing much light. So it's possible to have an ice planet relatively close to the star. And it's close enough that it's probably tidally locked, meaning it faces the star all the time with the same face of the planet. The same side of the planet is always facing the star. And that will, of course, mean that that side of the planet will get a little bit warmer than the rest of the planet. So possibly it's an ice planet, but the bit that's actually facing the star might melt and produce a little bit of a blue ocean. So hence a blue ocean surrounded by an icy world, looking suspiciously like a rather weird eyeball. So how do we go about finding these things, these exoplanets? Well, some spacecraft, such as the Gaia spacecraft launched more than 10 years ago and the James Webb Space Telescope, they were designed to do different things. Gaia is supposed to be mapping stars in the Milky Way. James Webb Space Telescope is looking at very distant galaxies and star formation, etc. But as it happens, they are both fairly good at finding planets as well. Gaia finds them by looking at small motions of stars. James Webb, as we saw earlier, can use an occulting disk to directly image exoplanets. But that's not their main function. Whereas various other space missions have been explicitly designed to look for or study exoplanets. Kepler found a lot when it was launched back in the noughties, the late noughties and early teenies. It found thousands of exoplanets. And you can see here from the dates that we have other space missions coming online. In the top right, a European Space Agency mission called Plato. Middle bottom, a NASA space mission, perhaps around 2027, called the Nancy Grace Roman Space Telescope. And in the much further future, in the bottom right, a Habitable Worlds Observatory. In other words, specifically going to look for Earth-like planets to see if they're inhabited. The one in the middle bottom there, Roman, let's just have a closer look at this. I said earlier that some telescopes will be directly imaging star systems and exoplanets by blocking out the light from the star itself and then looking for the exoplanets. That can be done with a disk inside the telescope, but one rather novel idea is they might also launch a star shade separate from the telescope itself. They'll detach the star shade, which will then unfold into a huge flower about 100 meters in diameter. And then they will fly this occulting disk a long way from the telescope, 50,000 kilometers away, such that it will be far enough away to block the light of the star, but allow us to see the planets that are orbiting that star. This, of course, will need a very careful choreography to make sure that everything is lined up accurately. Why would you bother making a large star shade and send it a long way away rather than having a tiny little disk and putting it inside the telescope? Well, if you can stop the light from the star getting into the telescope in the first place, you can reduce the amount of scattered light and you'll get better contrast and hopefully see fainter objects that are orbiting your distant star. So that's the plan. I mentioned that we might be looking for life. How do you go about looking for life when you're looking for exoplanets? Well, remember, exoplanets can transit in front of a star or go behind the star. And if you look at the spectrum of light from the star and the planet, even if you can't see the planet, if you look at the spectrum of all the light that's coming through, when the planet goes behind the star, you lose the light from the planet and the spectrum changes. And when you've got the planet in front of the star, if the planet has an atmosphere, then some light comes through the atmosphere and might be absorbed by any molecules in the atmosphere before the light arrives at Earth. So if you very carefully look at the spectrum of light, you might be able to see the signs of particular molecules. If we remember how transit works, we see starlight, and the starlight dips when the planet goes in front of the star. The James Webb Space Telescope has sufficient sensitivity that it can do that, and it can do that at various wavelengths of light. If we have a look at this box here and blow it up, we see the depth of the dip is slightly different for one wavelength, shown by the red dots, compared to a different wavelength, shown by the blue dots or the yellow dots. And if we choose the wavelengths that are likely to get absorbed by this molecule or that molecule, and we look at how much is absorbed, we can get information about what molecules are in the atmosphere absorbing the starlight. And this has been done for various exoplanet systems. So at various wavelengths, each dot corresponds to a wavelength in which they've tried to measure how much that dip was, and hence are we absorbing more or less at this particular wavelength compared to others. And we see a spectrum in which we see characteristic bumps that indicate, that looks like water, that looks like carbon dioxide, this looks like sulfur dioxide, this looks like carbon monoxide. We can see fingerprints of different molecules. So even if this planet happens to be thousands of light years away, we can still tell what the atmosphere is made of. That is technologically pretty amazing work. We haven't yet found signatures that tell us, yes, this particular set of molecules could only have been produced by life, but that is in essence what we're looking for. Do we see signs of oxygen or methane or other molecules which indicate that there are animals or photosynthesis or animals breathing and changing carbon dioxide to oxygen, etc.? Let me finish just by indicating what exoplanets have been found in a little animation in which a dot will appear at a particular location depending on the mass of the planet. So here we have the mass relative to Jupiter. So Earth would be down here and Jupiter would be up here. And on the horizontal scale, we've got the orbital period, how long it takes the planet to go around the Sun. So here are our planets for reference. So you can see there's Jupiter spending with a mass of 1, spending quite a few years going around the Sun. There's Earth with a mass of only a fraction of Jupiter, spending about a year to go around the Sun. So let's actually run this animation, and a dot will appear for every exoplanet that has been found. So in the 1990s, not much. But then, after measuring the wobble of a lot of stars and finding a lot of planets, then in the 2000s along came the Kepler Space Telescope, which looked for transit, and there's the purple dots appearing. So lots and lots of planets are now being found by the transit method as well as the wobble or radial velocity method. And you can see that now we're 2021, 22, 23, 24. This finished last year, this particular animation. You can see that we found thousands upon thousands of exoplanets. It's tempting to say, well, none of them look like our solar system because they seem to be planets that are up here, massive planets, but closer to the star, or perhaps not so massive, but they don't all appear to be in the same place as the Earth. And there are some planets with the same mass of Jupiter, but they all seem to be closer. Why are there no planets out here? Well, bear in mind that this might be a consequence of the fact that every exoplanet we find looks a little bit different than our solar system, but we also have to remember about the bias in our observations. When we're looking for wobble, it's easier to find massive planets because it makes the star wobble more. So we're not going to find it very easy to find very lightweight planets. And the same for transits. The bigger the planet, the easier it is to see the light drop because it makes a larger dip in the light curve. And the smaller planets, maybe they're going to be very difficult to see because they don't produce much change in the light. So just because we don't see many Earths doesn't mean they're not there. It simply means they are difficult to detect with these methods. And statistically, we have to be very careful in terms of making deductions about, well, we think we can see lots of planets like this. Does that mean that's what's out there? The bias means that we have a very biased view of how we see these exoplanets, but it is possible to take these measurements and deduce how many Earths there are, how many Jupiters there are, how did these exoplanet systems form. So I hope I've again piqued your interest about planets that are out there. Every exoplanet that has been found, all of its vital statistics, its size, its mass, its period, etc., they've all been documented and are available on the NASA web pages. They have an archive of how the planets were discovered and all of the characteristics of these planets that have been found so far. And the bottom three there, these are the missions that will be coming online hopefully before too long. The European mission in a year or so, and the NASA mission in a couple of years, as long as a certain president doesn't decide to cancel these missions. And in the long-term future, there are plans to build exoplanet missions to specifically start to find more of these Earth-like planets that we know are out there. Thank you very much.